In this code walkthrough, we want to look at one of the more underrated features of deep learning libraries, how we can compute gradients in PyTorch. Of course, we need this implicitly when we want to train neural networks. For example, it's part of the backpropagation algorithm, but we can make use of this explicitly via the AutoGrad module. And here we want to see how this works in principle. In this very simple example, we'll just take the derivative of a sine function where we also know the analytic solution. So we just go through sort of the mechanics of it because then it's easy to visualize. We can also then compare this to our expectation. Our training data function, and we add this between 0 and 2 pi, and you can see this is the sine function in this regime. Now let's start with defining a neural network. So we can start with a standard neural network, so a very small one. The key thing is that we have one input node, right? Because this is essentially our y values and one output node. So we want to use this function to learn y as sine of x, right? So we only have one node. And then we have a forward power. We'll just take the fully connected one with the tangents hyperbolicus as activation function and just have a few of those, and this is a very simple network model. Now we train our model, we have set up our optimizer, use Adam here, and then we have a standard loop. So we require now the training requires grad. So this is important because we want to track gradients, and we make our prediction for the model. And our data loss is essentially the sine function versus y train. And so here's the prediction, and y train is the standard between the training data as we had. Now the key part happens here. Now we take the derivative of the training data. So we use AutoGrad, from the AutoGrad model, the gradient, and take the output with respect to the predictions and input our training space. So this is really like here we take the derivative of the network. And now we have sort of a physics-based loss. A physics-based loss here in the sense means we want to compare this derivative of the network to what we know the differential equation is. And so for here we have dy dx. So the derivative of the sine function is the cosine function. So this is why we use a very simple example. So here we have the derivative of the network, right? And we know that this should be the cosine because this is what our differential equation. A more complex example would actually then put the differential equation here. And so we take this difference square. So this is then again taking the mean squared error of this. And now we have our data loss, which is essentially the predictions and the training data on discrete point plus our physics loss, where we say, okay, we take the derivative of the network compared to the differential equation that we know to be true, or that we want to model, whatever is more applicable in your specific case. And then we do the standard steps, and now the optimizer do the backward steps and so on. So we train this, and then we can plot the gradient. We can use again the AutoGrad module, right? And this is now what should be after the trained network results. This should be the cosine function. So we move all of this into the space where we can access them, convert it to NumPy and so on. You can see then here that you can even, with this model, you can't even see the sine function, the prediction gradient. They're all essentially where we need them to be. So we know that the module has computed this correctly.